All right, so Unit 2 is all about forces. This starts on page 108 of your textbook. And chapter 3 is on Newton's laws of motion. So this gives an indication that all the stuff we learned about motion in the first unit, we will still need to remember all that. But now we need to concentrate on why objects move, not how they move. So we're going to start with 3.1 and discuss what are the different types of forces. And you may have heard of Newton before, and you may have heard of Newton's laws, and that's great. So hopefully we'll build on your knowledge. Now, the one thing I want to let you guys know is I will try and pause, and I try not to talk too fast. But what you can do is use your little gear. If I'm talking too fast, you can slow me down, and if I'm talking too slow, you can speed me up to go at whatever pace that you want. All right? So we're talking about the types of forces today, and specifically this physics or aspect of physics is called dynamics, okay? And it's the study of why objects move the way they do. And the last one was how they move. So we discussed speed, velocity, acceleration. We'll still need to know those things, but now we're going to talk about forces. So what is a force? Well, a force is a push or a pull. And you might say, okay, well, how does a force do this? Well, there's two ways. There are actually contact forces. All right, and there are action at a distance forces. You might say, what is that? Well, contact means you actually physically have to make contact. So when you push your sibling, okay, when somebody bumps into you in the classroom, contact is made, okay? But action at a distance, no contact is made. I'm running out of space there, so I'm just going to try and squeeze this in right over here. So give an example of action at a distance. Something like, how about magnets? If I had two north magnets, these repel, and these two magnets don't need to make contact for them to experience that force. All right, so maybe I'll pause right there for a second. If you need to pause the video, I'm going to erase and get ready for the next board. All right, so here we are. So what, you might ask, what is the unit of force? Because I know that you, like me, want to know what your units are. So the unit of force is called the Newton. And you guessed it, named after the scientist. So a Newton is a derived unit. It's our first derived unit. What does the derived unit mean? Well, derived unit actually means it is made up of other units. So a Newton, which we indicate with a capital N, all right, is actually equal to 1 kilogram meter per second squared. And you might see this, and we're going to get into this later, but I'm just going to point it out that this is the unit of mass, And this is the unit of all of this, acceleration. Now, I haven't said anything about whether it's a vector or a scalar, but if you think about it, we talk about forces, which direction. You go complain to your parents, your brother shoved you. Well, what direction? Yeah, I would ask what direction. So when my kids fight, I'm just kidding. So here we go. Yes, and force is a vector. So we do need a direction. All right, so it needs direction. So that's that board. If you need to pause it, go ahead. All right, so the next thing you want to know is how to label a force. Well, if we look at the word force, A was the symbol for acceleration. F is the symbol for force. So use a capital F, do not use a lowercase. That's used for something else. And we need an arrow on top because it's a vector. So what we do is we use subscripts to indicate the type of force. So what forces do we know? Well, the thing that keeps you on the ground, the force of gravity. All right, so capital F, subscript is a smaller letter down the bottom right, and we have our vector. So what are some other forces that you might think of? Well, the other thing is what you can do. I often just put a subscript describing it. So this would be a pull force. All right. Another one that you maybe could think of that the textbook uses is tension. Now that one I do a little bit differently. Your textbook does this, but I find that that's confusing, so I prefer not to do that. So one that I do differently is I tend to use for tension. I actually use a T with a vector. So you might say, well, what's a tension force? Well, anything where there is a string or a chain involved in attaching to something. All right, a string, a chain, a rope. These would all be considered tension forces. All right, I'm running out of space. All right, so what about some other forces? Well, one that I'm sure you've heard of is the force of friction. So again, frictional force. I know FF. All right, so capital F, subscript lowercase f. Frictional force. Now this one maybe you haven't heard of before. It's called the normal force. All right, and it is a force that an object experiences I'm forgetting felt by an object. It wouldn't be a Goric lesson if I spelled something wrong. All right, so the normal force. It's a force felt by an object from a surface. So it has to be in contact with a surface. And what's interesting about this is the word normal. And I'm not talking about normal or abnormal. What I'm talking about is 90 degrees. Okay, when the word normal, you think 90 degrees to the surface that the object is in contact with. So we've done friction. Now, some people want to include air resistance in that. You can, or you can call this, it's any kind of friction, any type of friction. All right, so with air, And as we go, if we've missed one, we can always, add them. It's a different subscript. Now, your textbook at this point does discuss an equation for the force of gravity, which is mg. I like to leave that for when I do Newton's second law, but just in case you're reading along in the textbook, I want to, indicate this. It's not that I've missed it. And g is a constant. It actually has a number. It's 9.8 meters per second squared down. And maybe you've recognized this from before. It is acceleration due to gravity, but this is also known as the gravitational field constant. And we'll talk about some other units for that later. So I'm done here. If you need to pause the video, pause here and copy the slide. All right, so the next thing we need to know is something called FBD. I don't want to write this out every time, so we shorten this to FBD. It stands for free body diagrams. And it doesn't matter if you can't draw. It's actually pretty simple. There's not too much drawing involved. If you can draw dots and arrows, then you're good to go. So what a free body diagram is it shows all the forces that are acting on an object. All right, we use a dot to indicate the object, use a dot or a box to describe the object. And we draw arrows. Okay. We draw arrows on the dot or box. We draw these arrows away, okay, not towards. So we'll do a couple examples on the next slide, but essentially it could look something like this. All right, so this would be an object that has three forces, and that's not enough information, but this is essentially what a free body diagram is, and then I would label these forces. I haven't given a specific situation in this case, but let's say it would look something like that. So this would be an object that has three forces: the force of gravity, a normal force, and the force of friction on it. Pause here to copy. All right, so just to make this a little bit easier on us, what I'll do is the tutorial on page 117 has 3 examples, and I will do those for you. Now, your textbook talks about system diagrams. I tend not to do those, but I am going to show you here just so that you know the difference, okay? System diagram. It's essentially a more realistic picture. So question A, or example A, is a cup sitting at rest on a table. I would have called it a mug, but a cup sitting on a table. And I think that this implies rest. They actually use the word in it. I think that you should know if it's sitting there, it's not moving. So the system diagram would essentially look like this. Okay, here's your cup sitting on a table. But that doesn't help us solve the question. To solve these questions, we need to know all the forces acting on this object. So what do? You don't need to draw a mug. You need to draw a dot. This is your mug. And now we're going to indicate what are all the forces on the mug. Well, if we're on Earth, there's the force of gravity. All right. Now, if I look at this, we haven't talked about forces, but you could imagine if you looked at this, it would look like the mug is falling down. Well, the mug isn't falling down, it's sitting on the table. So there must be another force acting upwards. All right. And what's that force? Well, if it's sitting on a surface, it's that new force we talked about, the normal force. So it's Fn. Now, I want to get into a little bit more detail that the textbook doesn't talk about. Since this is sitting on a table and it's not moving, these forces are balanced. So just like in math class, I use these little hash marks to tell me that lines are of equal length because the length indicates the magnitude of these forces. All right, so I'll write that over here. Length of vectors indicates the magnitude, okay, or that's the number part. All right, and so in this case, the forces are balanced. And we want to talk about balanced and unbalanced forces throughout this. So forces are balanced. And how do I know this? Well, it's because the object is at rest. All right, so I'll keep saying pause here. You can pause here to copy this down. All right, so B. B is a situation where there's a trunk and the trunk is being pulled, by a rope. So a rope is attached to it, okay? But the trunk does not move. All right, so system diagram, which this is the last time I'm going to do it. It would look something like this, some kind of box and a rope and somebody pulling that. But like I said, not really interesting. And that's usually in the question. So I want to do a free body diagram. All right, so what are the forces? I'm just going to erase this hand. Maybe I'll put an arrow there. So that's a system diagram. So here's my box. Here's my trunk. All right. And there's a rope pulled. So that's a tension force. So there's tension. And in your picture, I have it to the right. You could have it to the left if you wanted. It doesn't really matter. Now, it's not moving. So if it's not moving, okay, the velocity is 0. This is telling us the forces are balanced. All right, so what other forces are on here? Well, it's on Earth. So guess what? Force of gravity. And if it's on a surface, there's a normal force. And now if I look at this, the forces are not balanced because I can see that there's definitely more on the right-hand side. Well, there must be a force over here, but that's not enough. I need to know what that force is. Well, if it's in contact, it's most likely the force of friction. And I didn't indicate that it was frictionless and, moving things in real life, unless it's on ice, that there is friction. But a lot of the time we do ignore friction, but not in this case. So here we are, there's 4 forces. The rope, this is the tension through the rope. Here's the force of gravity, the earth pulling down on the box. This is the normal force. This is the floor pushing up on the box, and this is the force of friction. That's a result of it being in contact with the surface. All right, I'll take a moment and write these down if I can fit them here. So this is the earth. Okay. This is the floor. Up, pushing up. All right, and the force of friction, and that's because it's trying to be moved. All right. Okay, pause. All right, our last 2 examples we have here, a baseball sliding into home plate and a table being moved. And the table is moving at a constant velocity. Now, your textbook didn't say that, but I'm indicating it because that's the only way it makes sense to me. So a baseball sliding into home plate. Let's think about that. So here's my person. All right. Now, if you're sliding to home plate, at some point you're going to stop. All right. So let's imagine that my baseball player is moving this way. Now, this is something that I do. I don't think you'll see this in a textbook, but what I like to do is I like to do a squiggly line. This is not a force. This is indicating motion. So the baseball player is sliding to the left. But which way is the friction? The friction is acting in the opposite direction. All right, so it's stopping you. And you think, well, but a force is pushing you that way. Yes, but it's stopping your motion, so you're actually moving to the left. Now, what are the other forces? Well, we're on Earth. So there's the force of gravity, and the player is in contact with the surface. So it's the normal force of the ground. So this right here is the motion. All right, now this person is sliding. They're slowing down. So we can see right here that the forces are not balanced. Okay. Forces are not balanced. Okay, so we call this unbalanced. All right, and last but not least, we have a table being moved, and it is moving at a constant velocity. So here is my table. It's being pushed. So it's F push. What's making it go at constant velocity? Well, there's friction. All right, and since we're on Earth, there's the force of gravity. And since it's in contact with a surface, force of friction. So I use 3 and 3 here just to indicate these are the same length, and 2 and 2 hash marks to indicate these are the same length. They're not necessarily all equally with each other, but they're definitely balanced left and right, up and down. All right. So I noticed that I missed some questions on page 119, so you could probably do those practice questions. All right, they're at the top of the page. All right, so hope you're glad to hear my voice. Maybe you aren't, but you can't tell me anyway. You guys can tell me in the comments in Google Classroom. Anyway, all right, hope everything's going okay. Let me know if you have any problems. I'll also do a solution to the sheet I put in Google Classroom, and I'll do another video for the next lesson. Bye-bye.